Hello. I have a presentation. If you would rather just like keep eating and drinking, that's okay with me.
You can eat and drink while you talk.
Okay, you're multitasking.
Yeah.
That's cool. So, about a week ago, I was like, hey, it looks like I'm not going to find a second speaker, so I get to be the second speaker. But I spend my days writing JavaScript, so I didn't have anything like just ready to go where I could just like take something from my work and talk about it. So I was like, okay, I gotta come up with something new. And so I decided that it didn't have to be serious because I'm not trying to get any real work done. And one thing that was a mystery to me for many years when I got into computers is like, so I understand some level of like how computers work, but there's like this just big mystery land of where somehow a typed in program turns into something that actually runs on the machine. And I can understand, you know, how a program works, and I can understand like how some of the electronics works, but there's like this big gray area between them. And I was working with computers for many years before I understood any of that. And it started, I kind of like dug into stuff when someone handed me a circuit board, and I plugged it. The only way to like get anything on it was to plug in a JTAG interface and like start poking away. I was like, how do I make it do anything? And it's a different process when you start out with a computer processor that doesn't have an operating system on it. It doesn't even like really have a bootloader on it. The memory hasn't been initialized yet. So you have to start poking data directly at CPU registers to say, hey, I want to use some memory. Can you make the memory available for me, please? And then you just start throwing data into it, and then how you actually like start stuff running is you set the instruction pointer, and you go, okay, I want to start running code starting at this memory location. But that was a long, painful process of like a month for me to figure all this stuff out. And I think for a lot of people, they don't have the time to just like poke at stuff that hardcore. But the thing is that machine instructions are not that complicated. It's just like, here's a byte, which is an instruction, and then here's a byte that's some data. And you know, on modern program processors, it might be multi-byte. But some years ago, I ran into this thing where this is machine instructions that correspond with ASCII values. And so, like on an x86 platform, the number 0 is actually an instruction, and the instruction is XOR. And 1 is also XOR. I don't know why there's like 4 of them, because it doesn't even like in this guide it doesn't even like say that like there are XORs of different like registers. They're just like, yeah, these are all XOR.
They're operating modes.
Different addressing modes.
Addressing modes? Okay. Well, this thing needs to be, you know, updated with better useful advice.
I'm guessing you weren't supposed to try to use it to write it somewhere.
Yeah. And so, but I mean, there's a lot of different things in here. There's compare, which like when you're writing a program, you always have like the less than, greater than, equal to, does not equal, you know, all these different things for comparing two numbers, but really internally on the processor, it only has one instruction for that. And what it does is it subtracts one from the other, and then it sets some flags of whether it is greater than or less than based on, like, when you subtract one from the other, do you get a positive number or a negative number? Or do you get equals? Or do you get 0, in which case it's equals. So you can get less than, greater than, and equals with just the same operation, because it's subtract one from the other, and then it sets flags. And so that's why there isn't actually like a greater than equals to instruction in the CPU. It's just compare, because it gets all those things for free, and you just read a status register and like find out like the specific thing that you want. And so it's actually like on the what situation is in that status register to decide what you do next. And then there's a bunch of, so this thing EAX, ECX, EDX, like all these things here, these are registers, which are basically variables with very boring names that you can't change. And and with like each, when you're writing a function and you like have some.
Plus, please.
Oh, make it bigger. Enhance.
Vertical holes.
Ah. Uh-oh, 2-bar.
No, it's perfect.
Right.
Leave it alone.
Oh, it just scrolled it. So when you write a function, you're just giving like a friendly name to, in some cases it ends up being a register, and sometimes it's a location on the stack, and the compiler just keeps track of where it stuck that data, and then when it needs it, it'll stick it back into a register in order to use one of the machine instructions. And so, like the I++, well, that's increment. So there's a plus operator, or actually there's like 10 of them. And then there's a whole bunch of them for decrement, and so it's just like it's a minus operator for all of your boringly named variables. And then push is putting it on the stack, pop's taking it off the stack. So that's a place for data that you don't need super quick access to, but or you have a bunch of it. And so you don't actually have in like things that you can type on the keyboard all of the instructions, but it actually turns out that there is enough that this is actually a website on hacking, and there's enough with just what you can type in on the keyboard that you can write a full exploit code that will pass the test that's testing for is like, does this look like something that doesn't have any crazy characters or binary? All these things that people do on websites and elsewhere to decide if something is safe. And you can write a whole machine instruction level program that passes all of these tests. And you can actually write a program that's actually really small, that's like 20 bytes, that will give them remote access to your machine if they get something to actually run it. Yes.
So a couple of follow-up questions. Have you ever tried writing a C program that is char star main equals a string? And if so, what was the longest string you managed to type in and still have a working program that didn't crash?
What?
You didn't know you could do this?
So think about what happens if you say, if you just define main. Main's just a symbol, right? The loader's going to load whatever's there. If you make it be an array of characters, right? Well, when the loader tries to load your program, it's just going to jump into that array of characters, right? And so, if you start taking your characters from this, right? Now you've written an assembly language program. The C compiler is happy to turn into an assembly language program for you, and the machine's happy to run.
Or try to.
Yeah, try to. It'll run it. I mean, whatever happens, happens.
Horrifying.
So how do you make that work? It's-
You write a C file with the contents char star main equals some string. You know, just a regular C declaration of a string to run the board, and you just compile it the same way you normally do cc-o ubar.
Of course.
Hit enter, /ubar, and maybe it will work, and probably it will crash.
The compiler will whine at you because it will say, wait, main isn't supposed to be of type char star, and then it will just, it's just a warning.
I've not tried that, but
Doing project is more like, let's build an ELF file from scratch. You know, not just let's use the compiler to build one and then have a funny way of
So
for man.
you're going past the whole like stack smashing thing,
well, so my thought is that I could write an assembler that I didn't have to do like all of the conversions of like what normal assembly does, but just used, you know, like a subset of assembly that you could do with just straight up characters.
All right.
Unfortunately, it's kind of hard to completely do that because as soon as you want to do something like write to standard output, you're doing a system call, and system calls use interrupt 80. So you need to get, let's see, let's try and get this big. So, and you need to get 80 in one of your registers so that you can do a system call that tells, hey Linux, could you do something for me? Because from your, with modern computers, you can't just like, hey, where's the memory address and hardware of the terminal output and write data to that. You have to ask the operating system politely, and then the operating system decides whether or not it should let you. You know, with if you have there's an exception if you're like running as root, you might be able to access something directly, but not necessarily because of like virtual memory anyways. But so problem is that 80 is not on your keyboard, and that makes things a little harder. There are ways around it with some people have come up with like crazy stuff. There is stuff in here on like how to write something that will convert something from something else into 80 so that you can get 80 on the stack so that you can do a system call. For example, you know, see these increment and decrement? So you can just call this character over and over and over again until you turn increment or decrement, you know, hit it a whole bunch of times. So you're just like, oh, I just need to take, let's say, like one of these bigger numbers, and so take z and just increment that a few times, and you get the 80 that you need, and then you can call stuff. So I was gonna do some niceties in order so that like a syscall was at least something you didn't have to do exceptionally convoluted stuff to do. But I was thinking of this in terms of a way of bootstrapping to get, you know, an assembler in assembler that, you know, my thought was like on systems where you don't have anything, what can you do if all you got is a terminal and you can't download anything? What can you do in order to actually like get full capabilities?
You want to be able to program your cell phone, is what you're saying.
Yeah, or whatever.
I don't know, my first thought would be to write ELF files by hand.
Yeah, well, you know. So, but I was like, okay, so if assembly programming is just like putting a bunch of characters together and then it runs it, then the problem then becomes like, how do I get stuff into a format that the computer will actually run? With that, a lot of the hacking approach is get the program that's already running, find a bug in it to get it to like set its instruction pointer to where you put in this chunk of stuff. And so they kind of avoid that step, and that lets them get an exploit that's in a matter of bytes. If you follow some of the security stuff, there's the size of some of these exploits is just so small. I don't I guess this is not an assembly code example, but with there's one of the top websites where the exploit that took down their entire thing was like 4 characters, and it was just like 4 characters in a username, and it was like quote or true or something. It's I don't know, some little thing where it was like, and when they set their username to that, and then they went and changed their username, and it stuck that in raw, and it goes change username to this where username equals, and then it says or true. So it changed all usernames in the system to what they just set it to, and then no one could log in.
So they're not compiling their SQL statements before they're running.
Yeah, so I mean, it's like, but I mean, like that's just like an example of where it's like the smallest, tiniest things, or like on the checkout page, it let them change the quantity of what they were buying in the checkout page, and they changed it to a negative number, and they're like, well, it credited my credit card. And then the shipping department still sent me stuff. Because negative number, that must be a dash or something. Because I can't ship a negative amount of product.
They sent you 4 million or 4 billion, whatever, negative.
I mean, like, I don't know. There's tons of stuff where it's like the tiniest little thing. So, but what I ended up doing was I was like, okay, so I just need to, since I'm assuming that I do have a command prompt, when hackers don't usually get that. They're doing this hacked in order to get the command prompt. How do I get a binary file without having an assembler or the ability to download or a compiler? And so I was like, okay, Wikipedia.
Help me, Google.
Help me. And this actually has a pretty good explanation of what the data should look like, and it's a significantly complicated thing where everything has to be right, or it'll complain and maybe not run. But I did some experiments with so I took Hello World in assembly for Linux, and I assembled it and made sure that it ran, and then what happened to my terminal? Seriously? Okay, I had everything I needed open, and then now it's gone. I don't have a workspace switcher. Oh, here it is. Why isn't it in my tasks? I don't know. Anyways, so I compiled it, and then I stripped it because otherwise it has a bunch of extra crap in the file that you don't actually need and complicates understanding of it. But there's this program called readelf, and it'll tell you a bunch of information about your file. And so in the header of an elf file, it has some things where it's says this an elf file, says what type of system, whether it's little endian or big endian, whether it's 64-bit or 32-bit, what operating system. Interestingly, there is a thing for Linux, but on things compiled on Linux, it marks it not as Linux but as Unix. At least if you don't specify. And then there's like a bunch of stuff on version, but they've never changed the version since whenever they came up with the standard. So everything is version 1 everywhere. And then they reserved a big chunk of, and almost everything is at least a byte as far as like the main header. They wanted to avoid bit addressing of stuff because that could be complicated depending on what processor you're on. And so almost everything is at least a byte, even if it's just a true false value in there. And so readelf tells you some stuff about it, and there's some sections in it, and the first one is null. I don't know why they bother with a null one, but there seems to always be there. The actual program is labeled .text. It's not labeled .code. It's not labeled instructions. It's text, but that is like the most binary part of the whole thing is the .text part. I don't know who chose that. And the .data in this case is the part that says hello world. So if you have data that just like exists in the program when it starts instead of something that it gets from somewhere, it's just loaded into memory. And so these are just like memory addresses of like where you should stick stuff. And I noticed like it has like this is actually a big number of where it sticks stuff, and I'm not entirely sure on why that is. It like says is like, oh, this is like 4 gigabytes out into memory is where you should load my program. But on a virtual memory system, it's the operating system's putting that wherever it feels like it. So I don't know why it has to be a big number. And then the world part is like put like 2 gigabytes away from that. Just because, I don't know why. But as far as like what the operating system's actually doing with that, it could be wherever. And then it has like a section for strings, and that's actually the labels .text, .data, .this. And I did some experiments with like taking this and then just chopping off the end of the file so that's not even in there, and it'd still run. You can actually like chop off a big chunk of the file or start hex editing it a lot and it'll still run. It might, certain tools might complain about it, but yeah. So I use that as a reference of like what kinds of things I should get out. And I just basically started like looking at this and I was like, okay, so the first part, the very beginning of the file, byte 0, is 4 bytes that is the magic value, which is hex 7F followed by elf. So if you actually look at this in You can see right at the beginning of the file, ELF. It's an ELF file. Woo! And so in a lot of Unix programs, like especially scripts, if you look at the very first line of the program, it has like shebang /bin /python or something, which is what program to run it in. And similarly with executable files, it just like has at the very beginning of the file like a way of saying, hey, I'm a this kind of file. And incrementally, I just started, let's see. Okay, magic. The magic is Xerox 7 ELF. And as soon as I wrote a file to that, actually, let me, I can edit this file and make it do that again. I need insert. Oh no. So as soon as you have the ELF in there, the file utility starts identifying it as an ELF file. And then I just like started adding in more things that it said I needed. So and comment like another part. And then it starts saying, that didn't actually add anything to it. Oh wait, I need to run it. Now it says it's ELF 64-bit, because the next little thing is like saying what type of system it was. And this made it easy to verify that I was doing the right things as I added more and more to the file format. And so after I have a few things in there, it's like, oh, it's a 64-bit LSB. I think that might be saying it's little endian. I don't actually know. GNU/Linux. And eventually I got, all these different things in there. And it's, I was like, oh, all these gets more stuff into it. But so it's basically going through the documentation and each one of these things that it says it needs, just going through and adding them to it. I was just like, oh, it's the hex code for this. So with a more serious thing, you'd have a thing where it would either have an option to switch between little endian and big endian, or look at uname and like, hey, what kind of system am I on, and pick the appropriate value. But for just trying to learn about this is just like, okay, can I get what is the right thing to say here? And there's lots of crap like this where it's just 7 unused bytes. Thank you, specification, for requiring me to stick that in there. Or the version number, which has never ever changed, and it's got a 32-bit number for the version. because the standards committees are really gonna go through a billion versions. I don't know. So like this is just like the part that like file looks at to like figure out like what even is this? This is the shebang part where it's just like saying it's an executable file, what kind of system it runs on. And then you start getting into stuff that's more specific, and this got really annoying when I got into like all this stuff. But these are like memory addresses, like how many bytes in is the things like this, these little tables of information. So these numbers are like how far in there, into how many bytes into the file do these start, and how big are they? I don't remember what flags was even for. And then I just like, this is crap in order to make it bash print it. And I tried to get this to work in like a POSIX friendly environment, and I could not get it to work. It's like I couldn't turn a hex value into binary for everything I tried. And eventually, as I got tired of writing stuff like this, so this is not only do you have to convert from a decimal value to hex, because it's on an Intel system, everything is backwards. So you have to reverse the whole bunch of them. And so I finally got around to writing my first function, which I did use some external utilities. I used sed and awk and printf in order to, and binary calculator, to make it so I could just throw in a number and turn it into an escape string that represented all that hex value that I could printf. And I am not going to try and explain that. That's just took me hours to figure out those 4 lines. But what that gives me is now I can just put in a number in as a decimal, and then I'd say how many bytes does the standard require me to have, and it'll just give me that number with that many bytes. And I made my function name really short because I figured I was going to be using it a lot. So my function is just h, as you can see up here. Function h for 2 hex. Although it's like 2 hex, little endian, reverse, garbage. And then all I have to do is take that and send it to a file. And I made it, originally it was just like putting it to standard out, but that can turn your command prompt to garbage if you accidentally don't pipe it to a file. So I was like, okay, it's safer if I send it to a file, and then I made it a variable so that theoretically someday I could have an option that says what file to write instead of always writing a.out. And then here is an example of, this is one of those magic values that I had earlier, and I just overwrote it because it's a global, and you can do that. So it's like taking one of these things that is like a big string of garbage looking stuff, and it's like, oh, well, now that I have my new little tool, that big string of garbage that's 8 bytes is just, okay, the number and 8 bytes. And then you also need those secondary. So the first part is just like what kind, where are the tables, how big are they, and then you have, which is this part at the top, which is like, so all those numbers at the top is just like this stuff, and then you get into these sections, and that's just like another little thing. And I was like, okay, so I just want something that I can see if readelf is happy with the way I'm writing data. So I just put in some numbers, and I stole them from the hello world assembled and stripped. And so I'm not actually like calculating anything here. These are just like, oh, I took these out of the other program, and to see if I could write something that readelf was happy with. And so eventually I'm going to have something that actually calculates correct values for that and goes through and makes all the sections that need to be there. And so if you actually look at, let's see, I don't know if I ran it since I uncommented all that stuff. What am I doing wrong? And so I actually got it to the point of where readelf thinks it's a real program. It only has one section because not looping through and making all the sections yet. I just have some fake data in there. And it goes, oh, and I got something to load into memory that is readable and executable. And that's as far as I've gotten, as far as making a assembler in Bash.
So what happens if you run it?
Well, this is what. So when I run it, it just generates the a.out. So it's just like it doesn't look like anything when I run
I
it.
mean, what happens if you run it and you got out?
Oh, I don't know.
Is there anything important on that machine?
Well, so it didn't mark it as executable. Change. So I take fault. Woo! So I made, before this talk, I made a new user on my system. So in this situation, with it doing random who knows, it was safe. Unless somehow it's so bad that it's running exploit code on me, it's safe. So yeah, I thought ahead. I'll make a new user, so I can't screw up my own stuff. It also means that if I accidentally, when editing my file and making it work differently while I'm talking to you, and I totally break it, I can't accidentally also, git commit it or, delete everything. Any other questions?
Are you gonna make it run?
I might.
It is in Bash.
It is in Bash. I mean, like it's like close enough to being done that
That's the second fault. That program don't work.
Well, I haven't tried to get the right numbers in there yet.
Maybe that's the program that segmentation fault quarterback is a hello world message.
I don't actually think you're very far from making it actually print hello world, man.
Yeah, it's pretty close. You should go.
Yeah. So I was gonna try and get it done for today, and I probably, if I hadn't done like day job work most of my time, I probably could have gotten it to working by now. But I was like, okay, I will be a responsible person, and only spend some of my time on this.
Why don't you run GDB on it and just assemble and start with text and see what
So it's been a while since I run GDB. What? Okay.
No,
Wait.
Just give it the argument, give it the executable. Okay.
So,
Disass, let me just say disass, it should be put in the right place, actually. Oh, no. Slash, disass slash, or whatever, slash.
Just saying
no.
it's all.
You need a slash for the text address, so, no, yeah, I think it has to be adjacent. No spaces, so just slash, whatever your text address is.
how do I find out?
Well, where did you put it? You should know this. Say slash,
400,000.
Yeah.
400,000.
400,000, yeah.
40,000.
40,000, where would you put it?
Um,
You better,
well, that was actually the disassembled, like, actual working program. So is
what yours is?
see,
You put it at the same place.
so you're saying this number?
Yep.
Okay.
No, you want the, what is?
Well,
Is it-
the virtual address is still the same, 400,000.
Yeah, it's the virtual address you want, but yeah, it is the same, so yeah, you should be fine.
So is it like 0x4?
Slash 0x40, yeah, slash 0x 40,000 or whatever. 400,000, wherever you put it.
1, 2,
5 zeros.
5 zeros.
Oh. Help disassemble, I guess. I've done this before.
So I mean, you can do.
You have to tell how many bytes you want to disassemble.
Oh yeah, there's that too.
Uh,
I like the other guy's suggestion, just run it, see where it crashes and
Yeah,
just
just-
disassemble.
Yeah, you can run it and just take a jQuery. Say
Yeah, just
GDB
go
and
to,
out
go
and
to
say run.
GDB and hit R.
Yeah,
so
just say run.
Boom.
Yeah. Oh, look at that. Now you got a frame. Now you can disassemble. Now if you say disass, it should do the right thing.
You do that whole address.
Oh, right, because there's an invalid stack frame here. No, this isn't going to help you.
Stack's gone.
Man, when I was a boy, we had
Backtrace
decent machine
gone.
level debuggers. Yeah, well, but you still should be able to find it. You just need to,
No, you
Maybe there
you
isn't
could
one
just
yet.
try something like x / 16x and then use the hex 16x
mhm.
and then space and then use 0x and 400,000. Let's just take a look at what's in memory.
That's a good idea. It's a good start.
There's your ELF header.
is it?
No,
Yeah,
that's,
7F,
Oh, yeah, it's backward.
right, because it's a little endy.
yeah.
So you could do it, 16B, and it'll do it byte by byte.
So if this is the ELF header sitting at 400,000, then something's wrong, right?
Yeah.
Because that should never, that shouldn't be there. So yeah, okay. Well, at least now we know what's going on.
Good work, good work.
It's definitely the most ambitious shell script I think I've seen in a while.
Well, what was your plan for actually getting it onto, if you actually had just a x86 board, how were you going to get it?
Oh, I mean, like this would be more like you get a command prompt on your Wi-Fi router or something, or your TV, because like everything has Linux in it now, and it's like, oh, here's. So you could probably make with something like a Arduino that has a USB interface or something where you make it emulate a keyboard. And then you can just like dump this in, and then you have on your system that you had a serial port in it. It's like, oh, now I have an assembler and something that's supposed to be a totally locked down system. And I have a way of like making a binary executable that lets me get to a lot of stuff that a shell command prompt would make difficult to get to. So it might actually be useful for some things where you want to like hack into something that's designed to be difficult to hack into. Of course, if you don't have a way of like writing it to file, that might make it hard unless you can figure out how to like exec something. But I mean, like you might be able to like write to /temp. That might be a valid thing where it's in a temp fs file system where it's actually an in-memory file system, and so it'll let you write to it even though it's a lockdown system. So there might be a way to do this.
Our modern system /temp is sometimes set. But yeah, if you have this kind of access, you should be able to just effectively use your shell things. You code take your assembler or whatever it is you want to move over there, you code it somehow, and have your shell script code. That way you can use cross-tools on the system instead of how you do this stuff. This is a good way to learn about how files work, about how assembly works, so about how machine works. So it's all good for that.
So when can we expect the ARM version?
Well, I mean, it's as far as ARM, I don't. It's been a while since I worked on it, so I don't remember if it's little endian or big endian.
Depends
But
on what you've got.
yeah, I think they actually like switched at some point.
Well, I'm playing with a particular baseboard management controller. It's a strapping option. So it's whatever they assembled it as on the board. It can either be big endian or little endian.
Yeah, I mean, like some of the ARM stuff can even has an instruction to switch instruction sets. So
Yeah, the thumb and what's the other one?
they're the ARM32.
Yeah, there's ARM instruction set, the 16-bit thumb instruction set, and they've got a Giselle or something like that.
Yeah.
Set, which is 8-bit.
Shouldn't they call that Pinky?
Well, so
But they didn't.
So it's called Giselle because it was a thing for taking Java bytecode instructions and running them as if they're native instructions in order to make them run faster so that you can run Java apps on your phone. But you needed to be like really special to have like any of the IP on it, and so it wasn't used as much as they envisioned because there's so much restrictions on even getting access to how to use it that people are like, I don't feel like spending $1 million today to make things.
Well, and with Moore's law, still crunching things down in terms of cost and speed.
Yeah, we'll
Just
just
run the Optima or the
normal Java.
Anyway, doing what you did with ARM is not very different, I think. Most of the ARM systems these days are alpha. You just build it alpha or you build somebody code.
Yeah, it's mostly so there's the lengths of these some of these big long things are different, whether you're 32 or 64-bit, and then instead of saying like it's probably still say Linux, still say version 1. Little endian might be 2 or 0. I don't remember what it was. So 64, that would be like a 1 instead of a 2. So it's just like a bunch of little changes,
Yep.
but the structure is pretty much the same. So it is designed to be versatile, which is part of why it has so many fields in it, because it's like specifying all that stuff.
So in terms of executing it, is the ELF, I mean, you could just have any, does it actually read that? I mean, I assume not, right?
So
It's just a file and other stuff.
So the ELF file is something that the operating system looks at and decides what to do with.
I
And
guess I'm saying maybe it's the magic, the stuff at the beginning.
The magic, the operating system will try to load it in all of this, that's what magic, that's what it's for.
Ah,
The
okay.
operating system looks and says, I know what that kind of file that is, because it has these magic 4 bytes of it.
Okay, so it checks that it's compatible.
Yeah.
With this hardware, okay.
Yeah.
But in this case, it's loading the magic too. That's what we saw there.
Right.
Yeah.
Yeah, that's probably where I got some like what location to load wrong.
Yeah.
So it loaded from the beginning of the file instead of,
Because first
100
it
bytes
complains something
in.
About not finding the text section.
Yeah, I saw in the help header that you had the load location set to 0, and that's not right. You need to set the load location. There's actually in the help header a load offset in the file, and you need to set that to the right offset.
Yeah, it's probably
If you do whatever your help dump thing is,
maybe this one where it says offset.
but it's a big string of zeros. It should be zeros anyway.
Yeah.
On the other hand, considering the GDB instruction point was somewhere off at 500,000, that implies that at least got through executing the up header. So congratulations.
Yeah.
Step 1. Any other questions?
Thank
Okay.
you.